Hello! I am so excited to go on this journey with you. Today, we are going to master one of the most powerful tools in all of mathematics, the derivative. By the end of this lesson, you will go from knowing absolutely nothing about this topic to solving complex problems like a pro. Our goals are to understand the why, master the rules, and tackle difficult combinations. Don't worry if you've heard this is hard calculus. We are going to break it down step by step. Let's start with the simplest possible idea: change. Imagine you are driving a car. At any moment, you can look at your speedometer to see how fast you are going. That speed is a rate of change. It tells you how your position is changing at that exact moment in time. In math, we often represent things with graphs. A derivative is simply a way to measure how steep a graph is at a single, specific point. We call this line, that just grazes the curve, a tangent line. The slope, or steepness, of this line is the derivative. So, whenever you hear the word derivative, just think, how fast is this changing right now? It is the instantaneous rate of change. Now, let's look at how we write this down in the language of math. Usually, we describe a relationship using a function, which we write as f of x. Think of this as the position or the value we are looking at. When we want to talk about the derivative, the speed of change, we put a little prime mark next to the f. We say this as f prime of x. This little tick mark is our signal. It says we aren't looking at the value anymore. We are looking at how fast the value is changing. Sometimes you will see it written as d over dx. This is just another way of saying the change in the function divided by the change in x. Don't let the different symbols scare you. They are just different names for the same idea. Let's start with the simplest rule possible, the constant rule. Imagine a function that is just a flat number, like 5. If you look at this graph, notice it is perfectly flat. It isn't going up and it isn't going down. It is constant. So, how fast is it changing? It's not. Its rate of change is 0. This gives us our first rule. The derivative of any constant number is always 0. Whether the number is 5, 100, or a billion if it doesn't have an x attached to it, its derivative is 0 because it never changes. Now we move to the most important tool in your toolkit, the power rule. This is for functions where x is raised to a power. Here, n is just any number, like 2, 3, or 10. To find the derivative, we follow two simple steps. Let's see it in action with an example. Let's look at the example where f of x equals x to the power of 5. Step 1. Take the exponent, which is 5, and bring it down to the front. Step 2. Subtract 1 from the original exponent. 5 minus 1 gives us 4. So, the derivative of x to the power of 5 is 5 times x to the power of 4. Let's try a harder one with a negative number. The rule is exactly the same. Bring the negative 3 to the front. Now, subtract 1 from the exponent. Negative 3 minus 1 is negative 4. See? Even with scary numbers, the pattern never changes. What happens if we have a number sitting in front of our x term? We call this the constant multiple rule. Don't let the extra number worry you. It just waits for us to finish our power rule and then multiplies the result. Let's look at 4 times x to the power of 3. We want to find the derivative of this. First, we look at the exponent, which is 3. We bring it down to the front, but there is already a 4 there, so we multiply them. 4 times 3. Next, we subtract 1 from the exponent. 3 minus 1 is 2. Finally, we multiply 4 and 3 to get 12. So, the derivative of 4x cubed is 12x squared. Take a moment to think about 10x squared. Bring the 2 down, multiply by 10 to get 20, and the exponent becomes 1. The derivative is 20 times. You're already starting to recognize the pattern. Often, functions aren't just one term. They are several terms added or subtracted together. This is where the sum and difference rules come in. The good news is that derivatives are very friendly. If you have terms added together, you just take the derivative of each piece individually and keep the signs the same. Let's look at this expression. We have three separate parts to deal with. Let's break it down. First, x to the fourth. Using the power rule, we bring the 4 down and subtract 1 from the power to get 4x cubed. Next, we have plus 5x squared. Bring the 2 down to multiply the 5, which gives us 10, and the power becomes 1. Finally, we have minus 7. Remember the constant rule? The derivative of a lone number is 0. Putting it all together, the derivative is 4x cubed plus 10x. We just ignore the 0 at the end. It's like doing 3 mini problems in one. Thanks for learning the sum and difference rules with me. Things get a little more interesting when two functions are being multiplied together. We call this the product rule. Here is the rule. The derivative of the left times the right equals the derivative of the left times the right plus the left times the derivative of the right. Think of it like a dance where partners take turns. You take the derivative of the first part while keeping the second part the same. Then add the first part kept the same while taking the derivative of the second part. Let's look at x squared times the sine of x. We can't just multiply their individual derivatives. We have to use the rule. Let's call x squared the left and sine x the right. First, the derivative of x squared is 2 times. We multiply that by the original right side, sine x. Now, we add the original left side, x squared, times the derivative of the right. The derivative of sine x is cosine x. And that's it. It looks longer, but we are just following a specific order to make sure we account for how both parts are changing at the same time. When we have one function divided by another, we use the quotient rule. I like to use a rhyme to remember this one. Low d high minus high d low, all over low low. High is the top function and low is the bottom function. The d stands for derivative. Let's try this with x cubed divided by x plus 1. Our high is x cubed and our low is x plus 1. Start with the low, which is x plus 1, and multiply by the derivative of the high. The derivative of x cubed is 3 times squared. Now subtract the high, which is x cubed, times the derivative of the low. The derivative of x plus 1 is just 1. Finally, put it all over the low part squared. We can clean up the top by multiplying and subtracting, but the hard part, the calculus, is already done. Now we come to the boss of basic derivatives, the chain rule. We use this when one function is tucked inside another, like a set of nesting dolls. Imagine you have a function like a shell, and another function inside it. To find the total rate of change, you have to find the derivative of the outer shell first, and then multiply it by the derivative of what's inside. Let's look at x squared plus 1, all raised to the power of 3. The outside is the cubing part, the power of 3. The inside is the x squared plus 1. First, treat the inside like a single block, bring the 3 to the front, and change the power to 2. Keep the inside exactly the same for now. Now, we look at the inside, x squared plus 1. Its derivative is 2 times. We multiply our first part by this 2 times. Finally, we multiply the 3 and the 2 times to get 6 times. So, the derivative is 6 times x squared plus 1 squared. You've just mastered the most used rule in calculus. Now, let's look at some special functions that follow their own unique rules. First up are the natural ones, exponential and logarithmic functions. The number e is a special mathematical constant, roughly 2.718. It is famous in calculus because it is the perfect function. The derivative of e to the x is just e to the x. It is its own derivative. This means the higher the value of the function, the faster it grows at exactly that same rate. It's the only function that stays exactly the same when you differentiate it. Next is the natural log, written as ln of x. The derivative of the natural log of x is just 1 divided by x. What if it's more complex, like e to the power of 5x? We use our friend the chain rule. We copy the function, then multiply by the derivative of the exponent. Simple and consistent. Next, let's talk about trigonometric functions. These describe waves and rotations, and their derivatives are beautifully cyclical. There are two main ones you must memorize, and they form a pair. The derivative of sine of x is cosine of x. When you look at how fast the sine wave is changing, it follows the pattern of a cosine wave. Crucially, when you take the derivative of cosine, you get a negative sign. Let's see how this works with the chain rule. Consider the function f of x equals sine of x squared. Here, sine is the outside and x squared is the inside. The derivative of the outside sine is cosine. We keep the inside the same. Now, multiply by the derivative of the inside. The derivative of x squared is 2x. Notice the pattern? We always deal with the outer shell first, then work our way in. Our final answer is 2x cosine of x squared. Up until now, we've had y on one side and all the x's on the other. But sometimes, x and y are tangled up together, like in the equation of a circle. We use implicit differentiation for this. The secret trick is this. Every time you take the derivative of a term with a y in it, you must multiply by y prime. Think of it as a mandatory tag that says, we just changed y. Let's find the derivative of this circle equation. We go term by term. The derivative of x squared is just 2 times. No surprises there. For y squared, we use the power rule to get 2y. But because it's a y term, we must attach y prime. On the other side, the derivative of 25 is 0. Now we just use basic algebra to get y prime by itself. Subtract 2 times from both sides, then divide by 2y. So the slope at any point on the circle is just the negative of the x-coordinate divided by the y-coordinate. By adding that little y prime tag, we can find the rate of change for any shape, no matter how messy the equation looks. What if we take the derivative of a derivative? We call these higher-order derivatives. The second derivative is written with 2 tick marks, and we call it f double prime. If the first derivative is your speed, the second derivative is your acceleration. It's how fast your speed is changing. In terms of graphs, the second derivative tells us about concavity, which is just a fancy word for which way the graph bends. If the second derivative is positive, the graph is a smiley face, or concave up. If it's negative, it's a frowny face, or concave down. Let's look at x cubed. The first derivative is 3 times squared. This tells us the slope. The second derivative is the derivative of 3 times squared, which is 6 times. This tells us how the slope itself is bending. Mastering this allows us to understand not just where a graph is going, but how it's curving to get there. Now that we have all these tools, what do we actually do with them? One of the most common uses is optimization. This is just a fancy word for finding the best result, like the maximum profit or the minimum amount of material needed to build a box. Look at the very top of a hill or the very bottom of a valley on a graph. What is the slope there? It's perfectly flat. Because the slope is 0 at these peaks and valleys, we can find them by taking the derivative and setting it equal to 0. This is one of the most powerful hacks in all of science and business. Let's find the peak of this frowny face curve. The derivative of negative x squared is negative 2x, and the derivative of 4x is 4. We set this equal to 0 to find where the slope is flat. Subtract 4 and divide by negative 2. So, the highest point on this graph occurs exactly at x equals 2. You've just used calculus to find the optimal point. This same logic is used by engineers to build stable bridges and by economists to maximize revenue. We've covered a lot of ground, and you should be very proud of yourself. Now, it's time for the ultimate challenge. We are going to solve a problem that combines almost everything we've learned. Take a deep breath and look at this expression. It might look intimidating, but remember our first step. What do we notice? I see 2 main parts being multiplied, x squared plus 1, all cubed, and sine of x. This means we must start with the product rule. We need the derivative of part 1 times part 2 plus part 1 times the derivative of part 2. To find the derivative of x squared plus 1 cubed, we use the chain rule. Bring the 3 down, keep the inside the same, change the power to 2, then multiply by the derivative of the inside, which is 2x. Now we assemble the pieces. We take that result and multiply it by the second part, sine of x. Then, we add the first part, x squared plus 1 cubed, times the derivative of the second part. The derivative of sine of x is cosine of x. Look at that! By breaking it down into smaller rules, product, chain, power, and trig, you solved a pro-level problem. You started with absolute zero knowledge and ended by conquering a complex calculus derivative. You now have the tools to understand how everything in the universe changes. Keep practicing and remember, calculus is just the study of change, one small step at a time. Congratulations!